두 번째 시간은 주제는 이제 데이터 인터로게이션 애널리시스라고 공지는 했었는데 저희 아까 앞에서 했듯이 주제를 저희 정했습니다. 저는 이제 패트릭 볼 박사님 소개를 좀 더 하고 나서 넘겨드리려고 하는데요. 좀 특별히 소개를 좀 더 하고 싶은 이유가 있습니다. 저희 어제 국제회의했던 자료집이 여기 여유분이 있는데 거기 안에 사실 오늘 스피커 우리 연사분들 프로필이나 뭐 어떤 연구를 하셨는지는 다 있고요. 뭐 이렇게 있으니까 참고해 주십시오. 제가 하고 싶은 얘기는 이제 이 부분인데요. 제가 패트릭 박사님을 알게 된 게 이분이 이런 분이 있다는 걸 알게 된 건 딱 10년 전이었었어요. 10년 전에 2014년에 저희가 단체를 만들 때였는데 만들 때에 저희가 하고 싶은 일이 뭔지 안 잡힐 때였었어요. 그래서 이제 구글링을 막 하다가 이런 그 휴먼 라이츠 크라임을 NGO나 아니면은 시빌 섹터에서 어떻게 해왔는지를 조사를 막 하고 있었어요. 그때 이제 캄보디아 기록센터의 육창 대표 캄보디아 기록센터의 일도 알게 됐었고, 그리고 이제 그때 알게 된 것이 오늘 휴이독스에서 우아지라는 소프트웨어를 얘기했었잖아요. 저희가 10년 전에 보고 있었던 게 마투스라는 소프트웨어였었어요. 그 마투스라는 소프트웨어를 1세대 First Generation 그 다큐멘테이션 툴이라고 얘기를 했는데 그 역사를 찾다 보니까 패트릭 볼 이름이 나왔었어요. 그리고 또 다른 케이스 스터디로 ICTOI 구유고슬라비아 형사재판소 관련되는 스토리를 막 찾아보니까 거기에 또 패트릭 볼이 나오는 거예요. 이분이 대체 누군가 싶어서 이분을 이제 프로파일링을 해보기 시작했었어요. 그때 보게 된 저희를 완전히 눈이 뜨이게 한 다큐멘터리 비디오가 이 Solving for X예요. 네. 처음에 저희 단체를 만들 때 파운더가 여기 댄 빌레펠드 씨도 와 있고 신희석도 있고 저희 동료들이 다 같이 이 다큐멘터리를 보면서 저희가 결국 이 길을 걸어가야지 되는데 이 길을 먼저 걸어가신 분께 배워야지 되겠다 생각을 했었어요. 맨 처음에 저희가 기금을 후원을 받고 첫 해외 출장을 패트릭 볼을 찾으러 갔었어요. 저희는 막 만들어진 단체이고 인터넷에 찾아도 한 페이지, 웹페이지 하나밖에 없는, 활동은 아직 없지만 하고 싶은 건 많은 곳이었는데 이메일을 드리면은 바쁘실 게 뻔하니까 저 비행기 티켓을 끊고 가겠다. 그래서 와라 하셨던 거예요. 그래서 이제 댄하고 저하고 배낭을 메고 팔로알토, 샌프란시스코 팔로알토에 찾아갔더니 그때 패트릭이 저희를 매우 환영해 주셨어요. 이날이었었어요. 10년 전이었는데 그때는 있죠. 네. 지금 여기가 이제 executive director를 하고 있는 메건 프라이스. 이때 패트릭이었었고 이때 이제 뒤에 있는 포스터들이 사무실에 가면 포스터들이 있어요. 그 포스터들에 뭐 과테말라, 라이베리아, 그 패트릭이 이때까지 그 도와줬던 나라들의 컬렉션들이 모여 있더라고요. 그래서 이제 그때 저희가 가서 저희가 이제 다큐멘터리 시작하려고 하는데 매핑을 하면서 뭔가를 하고 침해 사건들을 모아서 뭔가를 하고 싶어요. 어떻게 하면 좋을까요? 근데 저희의 질문이 이랬었어요. What to do를 물어보지 않았고요. What not to do를 물어봤었어요. 하면 안 되는 게 뭔지, 저희가 실수하면 안 될 거, 많은 시간을 버리게 될 게 뭔지를 얘기했더니 그때 패트릭이 저희한테 그런 얘기를 했었죠. 모은 기록들, 정보들, 진술들 아무것도 버리지 마라. 다 그냥 써놔라. 다 적어놔라. 데이터베이스를 만드는 건 나중에 할 일이기 때문에 잘 기록이 자세히 되어 있으면 구조를 만들고 데이터베이스를 구축을 하는 거는 뒤에 그걸 보고 할 일이다. 우리 맨 처음에 얘기할 때 오늘 힐덕스 팀에서 그 얘기했었죠. 뭘 갖고 있는지를 보고 빌드업을 할 수 있다고 했던 얘기 같은 얘기였었어요. 저희는 그때 마음이 급했었거든요. 뭔가를 빨리 첫 기금을 받고 2년 안에 뭔가를 빨리 만들어서 보여줘야 했다는 조급증이 있었는데 What not to do에서 아무것도 버리지 말고 처음부터 뭔가를 설계하지 말라는 얘기를 했었어요. 그래서 저희가 처음부터 바로 시작할 수 있어요. 제대로 시작을 할 수 있었고 2, 3년 지나서 저희가 처음에 그 북한 처형 매핑 보고서를 2017년 냈을 때 보여드리고 저희 점수를 매겨달라고 한 분이 패트릭 볼이었었어요. 이때 이제 서울로 패트릭을 초청을 했었죠. 2017년에 어제 국제회의에 7년 전에 제가 국제회의 있었다 그랬잖아요. 그때 어메싱 에비던스라는 컨퍼런스를 열었었고요. 지금처럼 이제 데이터 통계 전문가로 스태티스티션으로 모셨고 또 법률가. 그래서 어제 권호건 재판관님하고 Right. Yeah, I'll tell her. Well, you can tell the story. And Patrick here.
Valentina.
Valentina, yeah.
Okay. I will talk about her.
Got it. Okay, I'll give you the time then. 그래서 이때 트레이너였었어요. 트레이너. 그리고 트레이니였었어요. 저희 13개 나라에서 우리 북한 왜 자꾸 꺼지지? yours. 네. 이때 저희 원래 북한 인권 커뮤니티만 모였으면은 이렇게 확장되지는 않았었을 거예요. 저희 도너한테 북한 인권 그룹들이 다른 나라들 그룹들과 많이 우리 상자를 벗어나자. 그래서 13개의 다른 나라들의 사람들을 우리처럼 일을 하고 있는 사람들을 불러 모았었어요. 그 중에 한 명이 발렌티나였었어요. 트레이니가 그 다음에 만나가지고 같이 일을 하게 됩니다. 이게 너무 감동적이었었어요. 이 워크숍이 그때 7년 전에 했던 이런 워크숍이었었거든요. 그래서 이제 이렇게 설명을 하고 그리고 이제 다 같이 그때 워크숍 participants recognize them. 그리고 나서 발렌티나, 로저하고 패트릭하고 같이 co-publication 나왔던 거. You can.
And now she is the first author. This was the first edition. We've written 2 more. She's the first one. That is the happiest time for a professor. Is when your student goes on.
제가 이 얘기를 드리는 이유가요. 그때는 저도 이렇게 이어져서 또 다른 저희도 생각하지 못했던 콜라보레이션 또는 같이 일하는 동료가 될 거라 생각 못했었는데 보고 나서 저희가 이번 회의를 준비할 때도 이렇게 모아야 되겠다. 저희도 사실 이 HRDAG로 저희 스텝을 파견을 보내서 이 정말 이 아주 훌륭한 그거를 배워오고 싶은 생각이 있었는데 아직 가지는 못하지만요. 만약에 언젠가 또 모릅니다. 이 중에서 누가 또 패트릭과 캘리포니아에서 일을 하다가 또 돌아와서 이 운동을 또 바꿀지 모른다는 거죠. 이 스토리까지 하고 이제 패트릭을 연사로 모시겠습니다. 패트릭.
I'm or not. Wow, my goodness. When someone says you're a pioneer, they mean that you're very old. And he is correct. I have been doing this a long time, and it is a great pleasure to be continuing to do it, because every time I meet a human rights community, I am inspired by the bravery and the focus that we all have to bring in order to accomplish this work. It is hard, it is challenging, and consequently, I'll tell you a little bit of my story, how I got here, because I was inspired by the colleagues from HRDAG who did that. In the 1980s, I was a college student, and the political questions of the day in the United States for college students were apartheid in South Africa and the wars the US was supporting in Central America, in Guatemala and El Salvador. And I participated in the student political movements of the times. Soon enough, I decided to go to Nicaragua to see the revolution up close, and I lost all my politics. I was so disillusioned by the revolution. But I was left with a great sense of friendship and solidarity for the people, the individual people, the families who I met in Nicaragua. And I looked around and I thought, where are my politics? And I decided after a few years that my politics are very simple. Don't torture people. That's it. Those are my politics. That's it. Torture's bad. We can't have torture. Or arbitrary execution, or the forced recruitment of child soldiers, or disappearance, or wait, we need a list of these things. Hang on. We have the Universal Declaration of Human Rights. So those are my politics, and I've since that time tried to practice those. In 1991, I moved to El Salvador to work doing some other kind of political work, some human rights work, and soon enough, I was invited by the Non-Governmental Human Rights Commission of El Salvador, the CEDES, to help them build a database. I had been a computer programmer in the 1980s to make a living in mainframes and then later in small computers. That's what we used to call giant computers on the desk. I don't mean this, I mean. And we built a database that was very exciting. I told a little bit the story yesterday, but it was in some ways a distant ancestor to the great work that Security Force Monitor does now. And something happened in the course of that project that really caught me forever, and that is that we were able to create human rights dossiers for each of 400 military officers in the Salvadoran army. We were able to say what human rights violations were committed under the command of each of those officers. Now, throughout the civil war in El Salvador, we would have expected that they would have killed us all. We would have been disappeared. But because this happened a few months after the peace accords between the guerrillas and the state, the officers chose to sue us for defamation. So we went to court with the software, and I explained to the judge how the software worked. And after I'd been explaining for about 15 minutes, he stopped me. He called their lawyers up, and he said, "Get out of here. If I have to go through with this, I'm going to have to rule against you." So they withdrew their suit. Every newspaper in El Salvador said, "Well, the Cedes is right. Their evidence is correct." Because there was another mechanism inside the transitional justice process of El Salvador called the Comisión Ad Hoc. The Comisión Ad Hoc had the charge to depurar, or house clean, the military, to throw out the worst officers. And they used our list. I'm hooked. I haven't done anything in my life since. This is what I do, because I found a way to use the things I love, the human rights framework and technology, to accomplish what I think is a great social good. And that's why I'm still here 35 years later, because I haven't found a better game. Now, I want to be really clear, and I have a slide that'll say this, so I'm going to repeat this. I do not think statistics are the most important part of human rights. In fact, I think statistics may be the least important part of human rights. But if we're going to do statistics, they have to be right. And this is hard. It's really, really hard to do because we only have some of the data. And so we have to use sophisticated statistical models to understand what is the data we do not have. So that's what I'm going to be talking to you about. I introduced this a little bit in my talk yesterday. I'll review some of that today, and then I'll go into the software, and I'm even going to show you the code. So this will be quite a technical talk, and if people have questions, I encourage you to interrupt me. Okay? So let me go through it. But first, how do you do this work for 35 years? Okay? Now, one of the ways I do it is I go home and I cuddle my dogs. Okay? Because this work, and it's a silly slide, but I actually have a serious point. This work will hurt you. It'll hurt your heart. It's really hard to read these stories every day. Year after year, decade after decade, listening to the most terrible things that people do to each other. Okay? So it's really, really, really important that you find ways in your life to relieve that, to reconnect with your mission, with your vision, and with the tenderness and kindness that I think is at the heart of human rights work. But for me, it's my big silly dogs. This one is joining my family on Saturday. I'm very excited. I would stay in Korea for a few more days, but I have to go. All right. So let's talk a little bit about why we do statistical estimation. Okay? Sometimes people think, well, you have to estimate the unobserved total in order to get the big number right. Because every journalist wants to say 100,000 prisoners in North Korea or something like that. Okay, fine. We have to deal with that. But that's not actually what statisticians are focused on doing. What we're trying to do in professional mathematical statistics, our job is to figure out the range of likely truth. Not the number, not one number, but the range of that truth, in order to exclude the infinity of things that are not true. Okay? Because often, for the purpose of an argument, for an advocacy argument or a legal argument, it is sufficient to know the range. And so when we're constructing an argument, when you're thinking about what shall we say? It's really important to construct that argument in a way that respects our uncertainty. What is it that we don't know? Now, when I say uncertainty, I want to be clear. Uncertainty is finite. Uncertainty might be boundable. We can put a range on it. That's the point. So statistics is often described as the science of uncertainty. It is the science that studies what we don't know, but putting a structure on what we don't know, putting limits on what we don't know, so that we can still make arguments even with imprecise data. The reality is that our data will always be imprecise, especially in human rights, because both of the parties that know something about the violence have an incentive to hide it. Perpetrators hide the violence in order to create terror, in order to create impunity for themselves, and in order to shift the blame for violence to other people in society. Victims often hide and conceal violence because they're quite reasonably afraid of retaliation. Now, that makes our jobs much harder. Now, I'm not criticizing the victims. I recognize the validity and the importance of their decisions. But we have to, as professional analysts, we have to respond to that in a professional and scientific way. And so we have to limit the unknown. That's our goal. Now, I already said this, but it bears repeating, okay? If it's impossible to do professional good statistics, I will urge you to not do any statistics. Okay? An exercise I often do with groups that I'm working with is that I say, well, let me tell you what I would do if the police hired me. If I worked for the police, here's how I would discredit your argument. Okay? And it's valuable to go through this exercise to think about how will your argument be attacked in order to prevent that attack once you publish. So if statistics are done badly, even if they're a very small part of the report, that will be the place that gets attacked. That will be the place that people attack your report. Now, we work in human rights. We know that we are going to be attacked no matter what we do. People will attack us. But there's a big difference between a flimsy, poorly based attack that we can easily rebut and a very powerful, well-founded attack that may be right. Our job is to prevent really good attacks from coming at us. And so when I'm working with a partner organization, I often say very difficult things that are hard to hear, because I don't want my partners to be hurt by naive data analysis that they might publish. So let's get into it. This is a database from Kosovo. It's just a spreadsheet. And in the spreadsheet, test one, in the spreadsheet we have a list of names. And the problem is you can look up there, you can say, hey, you know what, some of these are the same guys. You know? It may be that Meho and Islam may be the same guy, maybe not. But we have to figure out which of these are the same people. Now, why do we have to figure that out? Okay? Well, first, we want to count every victim only once. Okay? That's the most important sort of starting point, is that you don't want to have a duplication of cases in your data because you just got more than one report of the same case. In fact, in some cases that are very well known, you may get hundreds of reports of that case. This is common, particularly when there's a really signal event that every group will focus on and there may be lots of media coverage and so forth. You'll get hundreds of reports about one event. Now, we do not delete these cases, but we do link them. We observe them and we bring them together. And we study them as a group, because the collection of these cases will be our basis for our estimates. How am I doing? What time am I ending? Let me make sure I'm paying attention here. Okay. 2:30. Okay, so I have 45 minutes. Okay, great. Here are some cases from Syria. Now, the names are sort of funny, and that's part of why I keep them here. These are funny names because we translated the names directly with Google Translate. And so some of these guys get named Muhammad Ahmed, vegetable thief. And it turns out that that is actually a name in some Syrian subcultures, but it doesn't really mean vegetable thief. Just like in English, when someone is named Smith, it doesn't mean that they work as a blacksmith. But it's just a funny name that comes from history. In any case, it turns out that Muhammad Ahmed Greens is the same name with just one letter changed. So that's the same person. So our clerk who goes through and reviews all the data has clustered these. So this is one person, here's another, here's another, here's another group. All of these people who have fairly similar names. And I put them together like this because this is the next step. In the first slide I showed you from Kosovo, you saw just the list. Here we have a list that's been organized and the same records have been clustered together, and we've put an ID number that joins them all together. Okay? Does everyone follow this? What's going on here? All right. It's going to get a little more tricky, so everybody put your seatbelt on. All right. Here's another country that I won't tell you what it is, because this is a live case, but it's really interesting because each of these records is now a victim. But look what we've got here. This is the part of the data that matters to me. Here we have 1, 2, 3, 4, 5, 6 sources, okay? And I have a 0 or 1 indicating if this person was found in this source. Okay? This is what I think your database has to be able to do. You have to be able to have at some point a way, this is called an inclusion vector, a vector of 0s and 1s that tells you where this person was included in the source. All right? So this vector, and then the collection of these vectors, this matrix, is the information that's going to enable the estimation procedure that I'm going to explain. Okay? But you've got to be able to get to here. Now, I went really fast over the part where we just join all the records together. Yeah, that's a whole other talk. So we can get to that another time. But once we've gotten to here, now we can do some really cool stuff. Because remember, we don't know what we don't know. Okay? And what we don't know is systematically different than what we do know. And I'm going to just kind of wander off on some examples here until Hubert throws me out. But one of the examples that I want to talk about is how old are people who have unknown ages? Okay? Turns out there's a structure to that. And here's how that structure usually works. Let me tell you a little story. Let's imagine that someone's telling us a story of a homicide. Someone killed by the police. Okay? A neighbor or a relative. And they say to us, "Why did they kill him? He was only 14 years old." Okay? We can imagine that story, right? All right? Now let's imagine a similar story where that person comes up to us and says, "Why did they kill him? He was only 45 years old." No one would say that. Okay, why? This has to do with the notion of salience, of relevance. When you have a missing age, it's an adult. Because children and elderly people, age is part of their identity. But once you turn early 20s into your mid-60s, it's no longer relevant. Now, why is that important? Okay, let's say we have a list of victims and half of them have missing ages. And we do an analysis of the ages that we know, and we say, my God, half of them are children. Okay, do you see the intellectual error we're making? The error is we are assuming that the people with unknown ages have the same ages as the people with known ages. And that's wrong. That's wrong. We will get a bad conclusion by making a bad assumption about missing data. Now, let me make it worse. What about all the people who are not in our database at all? Are they like or unlike the people we do know about? Clue, they're unlike. And what is the difference? Here's another little story we tell in our team based on a lot of experience. When a lawyer is killed at high noon in a city square, the entire world knows about it before dinner time. But when a farmer is killed 3 days' walk from a road at night, we will never hear about it. Sometimes people say, oh, technology, that fixes all this. Everybody's got a cell phone now, even people in rural areas. And this misunderstands how people in rural areas relate to people who are not from rural areas. One such person who misunderstood this was then Secretary of State Hillary Clinton when she came to Congo in 2009. I was working for the UN at the time. And she thought that one of the reasons that small Congolese villages when they were attacked by a militia, they never called the UN. She's like, well, maybe because they don't have cell service. Okay? And so the UN gave a truly vast amount of money to South African cell phone companies who covered Eastern Congo in cell phone coverage. You get better cell phone coverage and faster internet speeds in Eastern Congo than you do in the Santa Cruz Mountains an hour south of San Francisco. Okay? Like half an hour from Palo Alto. Nothing changed. Nothing changed. Still, those communities didn't call for the UN peacekeepers when the militias came. Why? Because rural communities know that nothing good ever comes from outside. And this is true in Congo, this is true in Colombia, this is true in Kentucky in the United States. All right? This is a thing. This is a rural-urban thing. So, information is complex. The structure of visibility is complex. And that structure of visibility is determined by 100 factors, some of which are universal and global across humanity, some of which are specific to that particular culture and region. But when we're thinking about data, when we're thinking about what we're going to analyze, you have to start with, why do we have this data? And what is it that we don't have? And if you think about it in terms of what has made this data visible to us, or to the data collection group, that will be your central intellectual tool for making this kind of determination. So again, I'm going to review a little bit of what I discussed yesterday and give you a few more anecdotes along the way. Let me check in. Is this all clear so far? I haven't showed any code. There hasn't been any math. Okay, it's coming. So we're collecting 3 databases, okay? And our partner organizations have shared this data with us, and we put the data together, and through the magic of deduplication, we've made them intersect. And so we know what cases are in between, all right? We know what's shared. Great. Which world do we live in? The white circles are the same. But we don't know if we live in this world where we only know a tiny bit of it, or we know almost all of it. Okay? We can't tell from here which world we live in. And it matters because it might be that different parts of the society have different reporting rates. In some parts of society, we might know almost all the cases because it's highly visible. And in other parts of society, for example, a different perpetrator, we may know only a small fraction of it. And you can see the intellectual error that we would make if we made the determination about responsibility simply based on the observed data. We would screw it up. And making determinations about responsibility for mass human rights crimes is one of the most important things we do. You can't afford to screw this up, especially at a truth commission. You got to get it right. So you have to take this into consideration. All right, more anecdotes. Here we go. So when I worked at the UN in 2009, 2010, a little bit of 2011, in Congo, one of the most important topics of the time was violence by a militia group that was originally from Uganda but was in northeastern Congo called the Lord's Resistance Army. Okay? Now, for those of us working in Congo, we had questions about why the LRA was so important, given that they were about the 7th or 8th most important perpetrator, but there was a whole subsection of the UN mandate, for the MONUSCO mandate for the UN mission at the time that focused on the LRA. Turns out we figured out why it is, and it was internal politics in the United States, but we'll leave that aside for now. We focused on the LRA. In fact, because it was important, because it was in the mandate, we had an office in a little town called Dungu, which is about 2 hours motorbike ride from Kisangani in the northeastern part of Congo. And this office in Dungu was focused on documentation of violence committed by the LRA. And I knew the people who worked in that office. They were among the most dedicated human rights investigators I've ever known in my career. They were amazing. Working in Dungu is extremely hard, okay? It's really hard. The physical conditions are very hard. People are people who are not from the region tend to be sick all the time. And the conditions are very difficult to access the villages that are being attacked by this militia. And you have to get on your motorbike and go there to do your investigation. All right. Now, if you work in a hardship zone of the United Nations, what happens? Well, every 8 weeks, you have to leave the country for 2 weeks of rest and recuperation. Now, I'm not complaining. This is actually a really, really important and valuable thing to do because otherwise people would psychologically break down. You have to do this. But let's play out what happens in the data, because I'm all about the data here, folks. All right, 4 people, they work really hard, and they document 100 cases in March. Great. And they send that, they write it all up, and they send it to Kinshasa, and we in Kinshasa process this documentation, and we send it on to New York, and the Security Council staff look at it in New York, and they're like, right on, 100 cases in March, got it. Thanks, team. All right, in April, 2 of the team members rotate out in R&R for the first 2 weeks of April. And the team works their ass off, because they still are working really hard, and they document 60 cases. And they write it all up, and they send it to Kinshasa, and we write it all up, we send it to New York, and New York is like, woohoo! Violence of the LRA is going down. Wow. Yeah, this is the level of egregious naivete that the most powerful and arguably most impactful institution in the world working in human rights is using on this stuff. Now, they knew perfectly well, because I wrote repeated emails about this, but it was inconvenient. Don't let this be you. Okay? If you're the Security Council staff, you can ignore all criticism because nobody's listening to you, nobody cares. People do listen to us. It's important. So don't make analyses that are that naive. You think I'm done? I'm not done. I'm going back to Congo for another example. Okay? One of the most important kinds of violence that occurs in Congo in the context of the conflict is sexual assault. And throughout eastern Congo, there were many, many, many women who suffered sexual assault, and as a consequence of sexual assault, they suffered a vaginal fistula, which is a very, very terrible injury, very painful, and it can be life-threatening. There is an important hospital there called Panzi Hospital, and Panzi Hospital developed specialists, and people came from Europe and the United States, and then Congolese surgeons learned how to do the cutting-edge, just best work in the world correcting this injury, vaginal fistulas. And women benefited from this. Great work. Nothing in my anecdote criticizes the hospital or the surgeons. But Harvard, yeah, so Harvard sent a team to review the records at Panzi Hospital. And they wanted to characterize statistically the pattern of fistula repair that the hospital had been conducting. And they discovered that somewhere around 2007, the number of surgeries that the hospital was performing declined. In fact, it declined like 66%. And they're like, wow, this is an amazing indicator that there's a decline in sexual assault in Congo. No. No, in fact, this surgery had become so important that European donors had created 2 more hospitals in the same region. Okay. We can't have this, all right? So you have to think about, why do you have the data? What do you not have? What's constructing the data flow? What are you saying with this data? And if you haven't asked those questions, then you probably don't know the answers. And that's a problem. All right, I got more. All right, so we're going to Iraq. And one of the most important data sources in Iraq is called the Iraq Body Count. The Iraq Body Count has done astonishingly important work. They started work, they're a London-based group, but they started work right after the Allied invasion in March 2003. And they accumulated media reports from all over the world. And to their immense credit, they accumulated reports from all the world's international media, okay? From all across Asia, from all across Europe, from all across the Middle East and North America and South America. They got over 200 major media sources that they reviewed every single day, and they extracted the lethal events of deaths into their database, and they deduplicated them in near real time. Breathtakingly important work, okay? very good work. And this is an extremely valuable measure of what the media pays attention to. So I'm not criticizing the Iraq body count. However, other people took the Iraq body count's work and used it as a proxy for the number of people killed in Iraq. And we knew this was a big problem because the media reports what the media sees. What they don't see, they can't report. So what happens? I asked Iraq body count for their raw data. And they gave me, after several years of negotiation, they gave me the data from the Februaries of 4 years. And from that, what I did is make this graph. And this graph represents the test. This graph shows, well, let me start off. I divided all the cases into how big the event was. So in the first bar, we have events with one victim, events with a single person, so very small, specific events. Then we have the second category of events of 2 to 5 victims, 6 to 14 victims, and 15 or more victims. Okay? And then in each bar, I've shaded by the number of sources that document those victims. Okay? So we see here in events of 15 or more victims that more than 3/4, in fact, slightly more than 80% of all the cases have 15 or more individual sources, independent sources. Okay? And only a tiny number of the cases have 1 or 2 sources. Okay? And as you move down to smaller events, you see that this fraction of very, very well-documented cases declines really quickly. Until when you get out here to the cases with one victim, you have 3/4 of the cases have only 1 or 2 sources. All right. Now, thought experiment. A case that is undocumented is a case with 0 sources, right? So what kinds of events in Iraq are undocumented? You can look at this graph and make a pretty good guess. Does anyone want to take a guess? What kind of cases in Iraq were rarely documented? These ones? Well, these ones have 15 or more sources. So they're pretty well documented. Look at this. We have 3/4 of the cases of individual victims with only 1 or 2 sources. So it's easy to imagine a lot more cases here with 0 sources. Right? Okay? Turns out there is a statistical method which is not especially great, but it's good enough for me to figure out that the probability of reporting for an individual case was only about 0.2. Only about 1 in 5 of the cases of individual victims were reported, but essentially all of the cases with 15 or more victims were reported. Now, why does that matter? Because small events and large events were completely different conflicts. Completely different things were happening at the same time. Small events were committed by Shia militias using firearms. Their victims were almost exclusively adult men, and their goal was ethnic cleansing. They were trying to drive Sunni people out of Baghdad. Okay? Large events were committed by al-Qaeda in Iraq or the coalition itself. They were IEDs or airstrikes or massacres. They had a random selection of victims, randomly selected, old people, young people, men, women. And the goal was either destabilization by al-Qaeda in Iraq or control by the Allied forces. Totally different conflicts. Which one did the international media pay attention to? This one. Which one did the international media largely ignore? This one. And what happened because we ignored this conflict? Oh yeah, ISIS. Right? All these people fled to Western Iraq where they welcomed ISIS. Why did they welcome ISIS? Because they needed security. Because they just suffered ethnic cleansing and had been driven out of Baghdad. And when people need security, they'll turn to anyone who will offer it. Now look, I'm not going to blame the rise of ISIS on bad data analysis, okay? That's a stretch. But look, we turn to data analysis to think about the world. We turn to data analysis to think about whether or not our observations are correct. And if we do data analysis in a naive way that reinforces our presuppositions, not only have we failed to learn something, we have reinforced our belief in the wrong conclusion. We have anti-learned. It is worse to read bad data analysis than have no data analysis. Because now you're convinced of your incorrect conclusion. I hope I've scared you enough. I'm going to stop with my examples, but I could go on all afternoon. And if there were beers in front of us, I would be hard to shut up. All right. Let's do some algebra. That's always bracing. Kind of gets us back into reality, right? Yeah. Okay, I did this yesterday. How many people would like me to review it? Okay, one. That's all it took. Here's the problem, right? The problem is we want to use math, probability theory, and some assumptions to figure out what we don't know. And what we don't know in this diagram is indicated by n, this whole big oval that's gray. Now, what we can observe are these two projects, A and B. These are the projects that have actually done the work. They've gone to the field, and we now have a list of deaths documented by Project A and a list of deaths documented by Project B. And again, we've done the deduplication that I've showed you, so we know what M is in between. Okay? And so now we have these three things we know, A, B, and M. We have a thing we don't know, N. So let's see if we can relate them. And we can relate them using elementary probability theory. Okay? So the first theorem of probability is that the probability of an event is the number of intents of the event divided by the number of observations, or the number of possible events. And there's some complexity to that. Are they repeated? Are they independent? Okay, just leave it there for now. So the probability that a death in the population N has been documented by Project A is A divided by N. Okay? Similarly, the probability that a death in the universe N has been documented by Project B is B over N. And because we know M, the probability of being in both data sets is M divided by N. But M is something else, okay? Because the probability of two independent events is equal to the product of the individual probabilities. So M over N is equal to A over N times B over N. 7th grade algebra, maybe in Korea 4th grade algebra. We rearrange the terms, and we get an estimate of N. AB over M is equal to N. Now, N gets a little hat, okay, which is the way that statisticians designate an estimate, okay? And that estimate is subject to variance or error. And I'm going to talk a lot about that in my subsequent slides. But the basic idea here is that we now have learned something that we didn't know before. We have some sense of how big N is. And this is our first little tiny handle on rejecting the naive data analysis, which I've been complaining about for the first 45 minutes of my talk. Okay? If you want to know more about it, here's an article that Megan and I wrote a few years ago, and it has a very, very, very long bibliography, so please be encouraged to help yourself to sleep. Okay? Okay? And now I'm going to start talking about software. Now, I put the full references in because I'm assuming I'll give these slides to TJWG, and then you can look at them and so forth. But the idea here is that there are two packages in the software language R. How many people here have used R? A few, okay. R is really my recommendation for most sort of classical statistics tasks. And I like it, and I'm going to show a little bit of our code. There's lots of other languages. Don't get stuck in Python. Keep going, keep going. And in particular, if you are really interested in data science, learn Julia is the language I recommend. But let's move on. And if you're really interested in data science, don't call it data science, call it statistics. Just saying. All right, let's move on. So this is a package called DGA. This is one of the approaches. And there are two approaches, both of which operate in a Bayesian framework. And a Bayesian framework is a new way to do statistics. It's not that new. It's been around since the 80s, but it's become much more popular and much more common, and there's very good reasons for that. And so both of the software packages I'm going to recommend produce Bayesian estimates. DGA is one of them, LCMCR is another. You can play around with them, and I'm going to show one example from each, I think. So now, what are we going to do? Oh, we're going to go look at code. Woo-hoo, yeah, all righty. Let's look at code. So this is a little program. Which one is this? This is DGA. So let's start with LCMCR. Okay. So this code, written by Valentina Rosso, okay, my very esteemed colleague. And basically, I put this up just to show that essentially the entire thing, once you've got the data organized, all we're really doing is making one function call. Okay? We're going to do one function call here, and we're going to do one more down here, and that's the end of it. and you've got your estimates. So the reason I put the code up is not so that you'll read the code, memorize it, and be able to use it later. No, you won't. But I put it up there because the actual estimation part of the work is very, very simple for someone who programs in this language. If you don't program in this language, I understand it's complicated, but this is for people who read and write in R, and I hope it will motivate maybe more of you to study reading and writing in R. So it's actually really, really simple. And what we get is right here, here's the sampler, this little section right in here, I guess the purple doesn't show up here. Here's the sampler, and then we call it here, and it runs. Okay? And that's it. And now we have the result. So what is the result? Thanks for asking. For a Bayesian, a result is called a sample from the posterior probability. What does that mean? We have, in the notion of Bayesian statistics, there is some probability of the result, the thing we're trying to estimate. In this case, the number of people, the number of women who suffered homicide by paramilitary groups in Medellin in 2004. So this is data from Colombia. And just this one municipio, Medellin, this one county essentially, in 2004, this is the possible number of women who suffered homicide. And what a Bayesian estimate does is it explores the probability of all the possible outcomes. And it tests to see, it checks number after number after number, literally millions or tens of millions of times. It checks lots of possible numbers to see if they fit in this probability space. And if they don't, throws it out and tries again. If it works, it includes it in the sample. And so what we have is this long list of numbers, which are all points that we observe in the probability space of the result. And when we make a little graph of them, this is what that graph of all those numbers looks like. We can see that there's a nice peak right here. That's probably the answer. That's it. That's the complexity here. That's probably the answer. But we can't rule out that the answer's here. And we can't rule out that the answer's here. But it's much more likely in here. That's very helpful. Because now if someone says there were 1,000 women killed in Medellin in 2004, I say, I doubt it. That's very unlikely. Someone says, oh, there was 100 women killed in Medellin. You're like, nope, because we have 350 names. But the idea is that the way I'm making this argument is all about this idea where we've got a bound around our answer. Okay? We know what the answer is, and not just a bound, we have a shape to the answer. Okay? And that shape is literally the probability, the literal interpretation of this result is that if the data is true, that is, if it is not lies, and if our models are appropriate, which statisticians spend their academic careers arguing about, but it is useful to know, and we can talk about that in another session if people are interested. If those two things are true, there is a 95% probability that the answer lies in this region. Okay? That's a very direct interpretation. For those of you who've taken classical statistics, you know, if you repeat the experiment 100 times and 95, okay, that's too complicated. My mind just melted. I can't figure it out. But this is quite straightforward. Okay? And that's the advantage of a Bayesian estimate, and that's what you get from this method. Okay? Now there's another method, LCMCR. It has pros and cons with respect to DGA, and I can talk about that in the Q&A, but I'm going to try to wrap up here. Because once we've done that for every year between 1985 and 2015, now you know where this little green zone came from. This little green zone is the 95% quantile inside that curve. Okay? And that's what this is. And it changes year to year because in some years the data is better than others. Okay? So, and there's lots of other factors that we can talk about that create the notion of error. Where does error come from? But in general, the point is, you'll notice I didn't write one green line right in the middle. I showed a cloud. Because I want to emphasize that we don't know the exact answer, but we know what the answer isn't. We can exclude lots of answers with this analysis. And then, I'm just going to show this again. Yeah, homicides and disappearances are not discrete. They are not distinct from each other. I think almost all disappearances are in fact homicides. And in fact, the law seems to anticipate that when it says, when the various statutes and treaties talk about acknowledgement or information that the authorities fail to provide. But I put this up because this is actually kind of complicated to calculate, right? To do this, you need to have all that deduplication done. To do this, you need to be able to find the same victim who's been reported in different ways in different data sets. Okay? So that's the end. I think there's 15 minutes for Q&A, and I hope this is useful to you. Oh, I was going to run the code. This is pretty exciting. Here we go. I'm running it. That's it. It's running. Oh my God, it's so exciting. It's still running. It may be running for a while. Let's move on while it runs. Are there questions? What do people think? By the way, this is the number of social movement leaders who were murdered in Colombia in 2016. Okay, here's the most likely. And this is from the first report that Valentina and I wrote. Our third version of the report will come out in October this year. The second version has been out for a while. So they're on my website, so you can find them there. And she sends her best. I signal messaged with her last night. She's like, oh.
Well, thank you, Patrick. Over here. Yeah. Well, first of all, your talk is always fascinating, and also very captivating as well. And I'm really glad that you have, when you met Valentina in 2017, it really blossomed into this really great joint work. So, again, kudos for that. I guess my questions would be like just you already mentioned like many like examples of applying statistical modeling to this kind of human rights statistical work, but can you also explain a little more about the Peru situation? I think you had the killings by the government forces on the one hand, and also the rebels, the Shining Path on the other, and I think that was on the graph, but and also this one, yes, and all. I think, yeah. Can you also explain again about the duplicating the enforced disappearances cases on the one hand, and the killing cases in the Colombian example?
Okay, so let's start in Peru. The challenge in Peru comes back to the thing that I started out with. It comes back to social visibility. Okay? So Peru is a country of many ethnicities, but for the simplicity of this argument, I will say there are indigenous people and non-indigenous people. Okay? Among the indigenous communities, there are several different ethnicities, and they are not even all that closely related, but for the purposes of social visibility, they tend to share a lot of invisibility from the point of view of not just the people in the capital, the non-indigenous people, they also are not very visible to each other, okay? Because some communities live in the Amazonian jungle, in the eastern and southern part of Peru. Some people live in the Central Cordillera, which is the big mountains, the giant mountains, very, very high, inaccessible mountains. And as a consequence, when you live on this mountain, getting to that other mountain is very hard. You may not communicate that much. Okay? And these killings happened largely in the 1980s and early 1990s, before cell service. Social visibility was compounded by a law in Peru that if you speak to Peruvians about their civil war, they will remind you that unlike the rest of Latin America, Peru was a democracy throughout their entire civil war. And one of the consequences of that democracy was a law entitling people to compensation if their families were killed unjustly by the state. Okay? So a number of NGOs were organized to facilitate the claims for compensation and to make legal claims against the state, which gave people a really good reason to document cases when their family members were killed by the state, which meant that nearly everyone who was killed by the state ended up in a database. So when we ran the Truth Commission from 2000 to 2003, people brought us their databases. We got a lot of cases about the state. Okay? Now, throughout the war, these NGOs had been denouncing killings by the state. That is our job. That is what we do. I'm not criticizing them by any means. This was what they did. But there was relatively less information about Sendero Luminoso. The killings by Sendero Luminoso were happening way up in the mountains. And most of the people killed by Sendero Luminoso were indigenous people who did not have strong communication networks with people in cities. And perhaps even more importantly, there was no incentive for anyone who had a relative killed by Sendero Luminoso to make any claim about it. Nobody was going to give you compensation. No one was going to protect your family from Sendero coming and retaliating against you for having denounced this case. And as a consequence, a small fraction of Sendero cases were documented before the Truth Commission. Now, Sendero was largely annihilated by the late 1990s, and by the time the Truth Commission started up, these communities were ready to talk, and so when the Truth Commission went up there, people told their stories. But we didn't get all the stories, by any means. The Truth Commission has a limited budget, it had limited logistics, and not every community trusted the Truth Commission. And those are all factors that govern social visibility. So we only had a certain number of cases from Sendero. Now, at the Truth Commission, they were freaking out. Because they had all these cases, nobody had any idea before the Truth Commission how many people had been killed by Sendero Luminoso. And the Truth Commission was like, how is it that we have all these cases? So they invited me to come and look at their data, and I said, you know, there's more. And they said, oh boy, that's a problem. So we did this analysis, and we discovered that, in fact, the reporting for the Peruvian army was pretty good. We had most of the cases. But reporting for Sendero had been relatively weak. We had a small fraction of their cases. So when we did the estimates, it turns out that Sendero had killed about half again more people than the army had. Well, this was a big conclusion. This was a big deal in Peruvian society. It's a bit controversial to this day. Because if you lived in Lima, you didn't see it. Right? What you saw was the government killing intellectuals. You didn't see Sendero Luminoso killing indigenous leaders, because that happened way up in the mountains, far away from TV stations, far away from lawyers. So there was no way for people to know. So it contradicted people's lived experience. Now, we should ask, why is there that lived experience? But this creates an interesting challenge. Now, I don't think it's as controversial in Peru today, but there are still people who are fighting with me about it. So that's the first of the stories. And the other story was, Ethan, remind me. Oh, right. Okay, so what we did in Colombia is we took all the cases of killings and we deduplicated them in one model. And we took all the cases of disappearance, kidnapping, and forced recruitment of child soldiers, and we deduplicated them in a second process. Okay? And then we linked them. We deduplicated across. Now, the advantage of this is that think about a kidnapping, which is very common in Colombia, or the forced recruitment of a child soldier, and a disappearance. Notice that the difference between these three, from the point of view of the family whose loved one is gone, is information. Okay? You don't know what happened to your family member. Were they disappeared? Were they kidnapped? Were they recruited by the guerrillas to be soldiers? You don't know, necessarily. You might know, or you might learn, because if you're going to go look, you're going to go try to find out, and you might figure it out, but you might not. So from our point of view, it's very difficult to tell those three apart. When we linked them across from homicide to the other three categories, that's when we could calculate the intersection between the two. Okay? And because at the root of all those violations is a person, is a victim, you have to build your models to be adequate to handle that linkage. And I believe the internet meme is now, don't ask me how I did it, I just did it, it was hard. So, but that's a whole separate talk. And it's a lot of fun, and there's some really cool machine learning stuff in there, and there's some really nice interaction between human training of machine learning models and how it is that we as human beings make decisions that we may make inconsistently, but a model can tease out and figure out and then apply at scale. And that's a kind of cool hack. Oops.
네, 안녕하세요. 통일망면협회 대표 김정아입니다. 지금 교수님 펼친 그 다음 슬라이드 좀 펼쳐주시겠어요? 다음 슬라이드. 아래.
This one?
Yes, thank you.
Oh, excellent.
아까 이 부분을 설명할 때 가장 저는 흥미로웠습니다. 왜냐하면 많은 데이터는 오히려 외부에서 다뤄준 게 상당히 많다. 너무나도 피해자, 당사자 입장에서 너무나도 공감하는 데이터 부분이고요. 특히 작은 데이터 하나의 문제 해결점을 진짜 우리 피해자들이 해결하고 싶은 문제예요. 이것이 가장 그동안에 많은 모순을 좀 겪었던 걸 저는 피해 당사자로서 너무나도 많이 안타까운 사례인데, 지금 어떤 상황이 하나가 있냐면 직접 경험자가 정신질환으로 증언을 할 수가 없어요. 그리고 오히려 521명이라는 그 수많은 피해자들이 50%에 넘는 사람이 이 피해는 반드시 있습니다 라고 말하는데, 이들이 직접 피해자가 아니에요. 목격자 혹은 간접 증언자예요. 이런 사실이 있는지 들었습니까? 그 당사자가 너무 없어서 우리가 데이터에다가 이런 피해 사실이 있는지 혹시 들은 거 있나요? 라고 한국에 있는 탈북 여성 중국 남편과 중국 안에 있는 중국 남편과 인신매매로 살고 있는 탈북 여성에게 다 같이 물어봤는데 거의 대답이 동일했습니다. 이것은 사실이다. 근데 피해자가 없어요. 그럼 결국은 저한테 지금 있는 거는 직접 증언한 피해자 당사자 데이터는 없는데 간접 데이터가 지금 있는 상황인 거죠. 교수님 입장이라면 이 데이터를 어떻게 활용하시겠습니까?
I love this question. I love this question. So, what this question does is it opens another aspect to how a Bayesian statistician thinks about a model. Okay? So, all statistical models make subtle but complicated assumptions about internal probabilities inside the model. Okay? So, for example, let me give you just one kind of simple example. When I'm making an estimate of the total, I may have to, as part of specifying the model, writing down the math, I have to say approximately how much do I think is missing and how wide is my uncertainty. I may say that I think there is 0 probability that there are 0 missing, there's this much probability that there's 100 missing, and there's this much probability that there's 1,000 missing. So I have a nice curve around that. Okay? Now let's talk about what would happen in different contexts. Let's say that I have this, it's called a Bayesian prior. Okay? And this is my prior, right? It goes, has a nice shape here. Let's say that I go out and do my study and I get 0 data. I get nothing. My conclusion is the same as my prior. I have learned nothing. Okay? Now, let's go to the opposite extreme. Let's say I go and do my study, and for whatever blessed event that has occurred, I learn everything there is possible to know in the world. I learn everything. Well, now, my prior is completely irrelevant. It has no effect on my conclusion because now I know everything. Of course, all real studies are in the middle of these two extremes. And in all statistics, the conclusion is a complicated mix of what we started out thinking was true, mixed with what we learned in the study. Formally, the posterior probability is proportional to the product of the prior and the likelihood. So if you take a Bayesian statistics class, this will be your mantra. The posterior probability is proportional to the product of the prior probability and the likelihood. The likelihood is the data and the model. And the prior probability is this curve that I've assumed. Where does one get such an assumption? Well, thank you for your question, because you've just described one of the places we might get such a prior. When I'm constructing a prior, I elicit from my partners what they think is true about the world, because I trust them, because my partners are immersed in the reality. They know what's going on. Now, they may not think with a statistician's mind. They may have another discipline that they think about. They may be anthropologists or psychologists or journalists or lawyers, but they know a lot. And it's my job as the statistician to try to hear them and convert their hearsay into a prior probability that we can use in the model. Now, again, How much impact that prior probability has depends on the quality of the data. If the data is terrible, we haven't learned very much, our conclusion is the same as the prior. If the data is excellent, the prior probability becomes irrelevant, and our conclusion is driven only by the data. But all statistical models have this character. All statistical models of all forms have these subtle probability distributions built inside. For a Bayesian statistician, we think our job is to make them completely and absolutely explicit. And then the magic science word here is we parameterize each of those. That is to say, we write them down and we show them. We say, this is how big I think it is, this is the shape it has, and here is its center point, and here is its width. Okay? And we say that for each of the parts of our model. Now, if you don't know anything, you can use very, very simple priors that maybe don't affect the model very much. I don't like that. That's not how science works. We don't start from knowing nothing. We start from knowing something. And so when I build models, I use what are called informative priors, which are informed by stories exactly like what you just told me. That's how we use that stuff. And it's really, really valuable. It's absolutely essential because it's one of the various ways we ground the model in the subjective reality and experience. I don't mean subjective like mushy. I mean knowledge held by subjects. Knowledge held by people is what I mean by subjective, as opposed to objective, which is knowledge that's outside of individual people. And I know there's postmodernists who will fight over that particular conversation, but I think there is such a thing as objective truth, and I will fight to the last beer over it. Anyway, so that's how we would use it. Thank you that was a great question. Is there anything else? I am at my time, and I don't want to be too abusive.
Just say the last person.
You could catch me.
Okay, I'll make it short. Hi, I'm April from TJWG. I think earlier in your slides with a list of names, and if the information is all identical and a slight variation in their spellings of their names, if I'm understanding you correctly, you can say like these two people are the same person. We've actually come across data like this a lot in our interview and when we're making the database. So like for example, if person A and person B have like one spelling difference, same date of birth, but then slightly different occupations, slightly different description of disappearance. So like right. So there's so many different factors.
So many.
So would it be a judgment call for the documenter, or I just wanted to hear a little bit more about what your take on this matter?
So that's the talk you didn't invite me to give on record linkage. But I'll take a few minutes to talk about what I think the right answer is. Okay? Let me start with the wrong answer. I have two records. They're pretty similar. They're the same. No, they're not. They're different. No, they're not. There's some probability of both. Now, this field, should you choose to look it up and start studying it, has been around since 1969, and it is called probabilistic record linkage. And the reason it's called probabilistic is because our goal is not to say yes or no. Our goal is to assign a probability that any pair of records refer to the same person, which is to say they are co-referent. Okay? So you're trying to assign a probability that any pair of records is co-referent to the same underlying person. Okay? Cool. How do you get there from here? Human beings do this. Not to all the data, but to samples of it. Okay? And from this, we build machine learning models that look at every pair. Okay? And we train those models based on human training data, stuff that human beings organize like this for a few 100,000 records. I mean, we do a lot. But in Columbia, we were starting with 26 million inputs, so we had a lot of records to deduplicate. And we looked at hundreds of thousands of pairs. But human beings don't look at pairs. Human beings look at clusters like this. You get a chunk of records, and then you organize them. From that, we extract the pairs And from that, we derive similarity measures. Okay? So a similarity measure, for example, is I have two names. How many characters does it cost to transform one name into another? That's a similarity metric. Here's another one. What if I transform both sequences of names into their phonetic representations? How many tokens different are they? That's another similarity metric. Here's another similarity metric. Let's say I break it up into 3 character chunks, and I put the character chunks in a bag, and I have 2 bags, one for each name. How many chunks intersect? That's another metric. In fact, we derive hundreds of similarity metrics for every pair of records. Now, they're the same similarity metrics that we apply to every possible pair, but that gives us, for all the possible pairs, a way of measuring for all these different fields, for dates, for locations, for names, for text strings. Now we can do all kinds of cosine similarity on vectorized data, just to throw out some little bit of jargon. You can then get all these measures, and because you now have a whole bunch of measures, and for some records a dependent variable, you can just train a model. Now, it's not a linear model, but it could be. You could use logistic regression. It's not as good. There are better models, but that's the idea. Okay? And once you have a logistic regression, or anything else that makes a prediction between 0 and 1, you can interpret that prediction between 0 and 1 as a probability of similarity. And then you have to test for whether or not your model's any good, which means you reserved a bunch of data and you use that as test data. So it becomes a kind of classic machine learning problem where you have training data, you have testing data, and you test fit. And then you go back and adjust your feature set, which is to say your similarity metrics, or you add training data until you're comfortable with the quality of your model. And once you're comfortable with your quality of your model, you predict for all the pairs, and then you do clustering on top of that. Okay? And clustering is a way of resolving something called transitive closure, aka snakes that eat their tails, the Ouroboros. Because you don't want your data to become an Ouroboros. What does that mean? Record A has a high probability of being like record B. Record B has a high probability of being like record C. Record C has a high probability of being like record D, but record D is nothing like record A. Uh-oh. Okay? Okay, you cannot assume that there's a transitive relationship in this whole set. So, you do something called hierarchical agglomerative closure, is the algorithm that's used from computer science. This is an old algorithm. It's from the 80s, I think, early 80s. It's an expensive algorithm. For those of you who know, it's O(n) cubed, which is bad. That you have to figure out how to reduce your problem, but this is why we have programmers. We have programmers for other reasons too. Yeah, sometimes they'll buy you beer. But that's the basic logic. The basic logic is you convert pairs of records into a single vector of a similarity metric. You use that vector of a similarity metric to train a model based on a dependent variable, which comes from training data that looks like this. Okay? That's a whole nother talk, longer than this one. And there's many other steps but all the other steps are about managing computational tractability. The problem is that in order to do this, you have to compare every record to every other record, which means you have a problem on the order of n squared. It's actually n times n minus 1 over 2. Let's not pick nits. It's n squared, which means that you have trillions of calculations very quickly. And yeah, that's not going to finish in any time that we can wait for. So you have to figure out how to split the problem up into little pieces so that you can actually do the calculations in a reasonable time frame at a reasonable cost. Sure, sure.
네, 시간이 많지 않은 것 같은데 먼저 오늘 발표 아주 흥미롭게 잘 들었습니다. 제 질문은 지금 선생님 발표하신 게 이제 베이시안 스태티스틱스를 베이스로 해서 현재 우리가 관찰한 게 있는데 그 관찰이 나올 수 있는 포퓰레이션이 어떻게 되느냐라는 것을 추정하는 것 같아요. 제가 바로 이해했는지는 모르겠는데, 근데 일반적으로 이제 베이시안은 사전 확률을 거기에 likelihood를 곱해 가지고 사후 확률을 계산을 하지 않습니까? 근데 지금 말씀하신 우리가 관찰한 것은 에비던스에 해당이 되는데 지금 아까 디스트리뷰션을 도출한 이 과정이 베이시안 관계식하고 어떻게 연결이 되는지 그 부분이 잘 이해가 되지 않는데 설명을 좀 해주실 수 있나요?
Yes, may I ask you a clarifying question? Do you mean the formal distributions that we use to parameterize? Do you mean why do I choose a log normal or a beta or a I mean, or-
No, what I'm asking is based on the Bayesian probability relation, that's starting the prior
right?
and multiplied by likelihood, then we will get posterior probability, right?
Yes.
So you estimate based on the evidence, the population distribution, right?
Right. That's the posterior.
Right.
Right.
So how can you make a connection with the Bayesian formula?
The Bayesian which? Sorry.
Formula.
Formula.
The relation.
Okay, well, the prior is what I talked about before. So I elicit the subjective understanding of experts, and from that, I can describe a prior.
Okay.
So that's where the prior comes from. Okay? The likelihood comes from the form of the model that we're using, and I've given you 2 papers here that you can have a look at how those models are formulated, that then are used to sample from the likelihood space given the data. And so the data and the model enable us to sample from the likelihood space in a way that allows us to estimate the posterior.
Okay.
So I think that's probably about as far as I can go here without like starting to do the math on the board. But I've given you 2 papers those both of the software packages that I proposed have one or several academic papers underneath that will give you all the mathematical detail you could ever hope for there. And I encourage you to read the code, at least our code. I don't know the other one. The LCMCR code's pretty hairy, but the code we wrote I think is kind of cute. It's nice.
My question is whether there is a simple way to understand, not reading difficult paper.
Oh, sorry, simple. Yeah, I missed the word simple. I don't know how to get too much. I mean, I gave the simplest explanation I could. Someone smarter than me could probably give you a simpler one, but the way I think about it is the prior probability is what we think is true before we do any study. The likelihood is the data mixed with whatever our reasoning is about how the model works, about how the actual process works to make an estimate about the world. Okay? And by multiplying those 2 together, we get the posterior. Okay? But the multiplication is a little bit tricky because it's weighted by the quality of the likelihood, the strength of the likelihood. So the stronger the likelihood is, the less the prior has any effect. And the weaker the likelihood is, the stronger the prior's effect. They balance out.
Okay.
I'm sorry that's maybe not as helpful.
Thank you.
Otherwise, I mean, yeah, I'm stuck. All right, I'm done. Thank you.